You're welcome once again to Simplified Maths class. And today we'll be going into set theory part 2. In the last part of the set theory, we were able to handle the introductory part of set theory, and we went in as far as treating the basic set operations that has to do with the union of sets, the intersection of sets, the difference of sets, and the symmetric difference of sets. And so today we'll be going straight to what we call the complement of a set. Complement of a set. Now, the complement of a set A, the complement of a set A with respect to the universal set, with respect to the universal set, capital U, is the set A complement, which contains all the elements in the universal set but not in set A. Now, each time we want to define the complement of a set, we must always do that with respect to the universal set. What's the universal set? The universal set is the overall set from which every other subset is derived. So it means that when you're giving subsets, you unite them together, they should be able to give you a universal set in most cases. So look at it this way. Now, for instance, assuming you're giving the universal set, capital U, and they say the universal set is a set of elements 0, 1, 2, 3, 4, 5, 6, 7, and 8. And you've been given another set A. Now this set is subset. This is the universal set. Subsets are derived from the universal set. Now you're given another set A. The set just contains the elements 1, 2, 3, 4, and 5. Now assuming you're asked to find the A complement, that's A raised to power 1. We either use this as complement or we use this. A raised to power small c. So assuming you're asked to find the A complement, which is this or this, sometimes you call it A prime, A complement. It means you're looking for the set of elements that are in universal set, but you cannot find them in set A. The set of elements in the universal set, but not in A. It means that if I take 1, 2, 3, 4, 5 from the universal set, if I delete 1, 2, 3, 4, 5, from the universal set, the leftover elements in the universal set are what we call the complement of A. And that will be what? 0, 6, 7, and 8. So the elements that are left in the universal set, when you are taking out the set A from the universal set, is what we call the complement of A. And that's why we say the complement of a set A with respect to the universal set is a set of elements A raised to power 1, which contains all the elements you see in the universal set, but you cannot see them in A. So the elements I see in the universal set 0, 6, 7, 8, and I cannot see them in set A, denotes the complement of that set. Now you should understand that complements, most times you view it almost the same way you view difference of sets. But the only difference is that when you are looking for the difference in set, you compare set A and set B to find their difference. You don't make reference to the universal set. But when you are looking for the complement of a set, you are comparing that set with the universal set. So you are not comparing the set with another set. You're rather comparing it with the universal set. That's the difference between the complement and the difference of set, even though they have similarities, striking similarities. But that's just the striking difference. Okay, now that we know what the complement of a set is, we can now go ahead to solve a problem that has to do with complements. Now, let's take an instance. A problem might come this way. They say, given the universal set, all right? Or maybe let's not use this. There is another symbol we use for the universal set in case you see it, so that you don't get confused. So this is another symbol for the universal set. So giving the universal set to be the set of elements 1, 2, 3, 4, up to 10. And now the subsets of the universal set, or let's say the subsets A, B, and C are defined as follows. That means A, B, and C are subsets that are extracted from the universal set. So they might give you A to be, let's say, 1, 3, 5, and 8. And then B, they can say prime numbers. And then maybe C, okay, let's say 2, 3, 8, and 10. Now, they define the subsets of that universal set as A, B, and C. Now, some certain questions might come. You might now be asked to find, for instance, they could say you should find A union B, all complements, A complement intersection C complements, and then maybe B complement symmetric difference C. All right, you can see that this problem now contains almost everything we have done in the first aspect of set. So we are going to apply them right now. So we are going to define the universal sets. Define A, B, and C. That's the first thing we are going to do. We'll define them. All right, so let's define the universal set. So the universal set contains elements from 1 to 10. From 1 to 10. So let's define it. So we are bringing out the universal set, which contains the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then we are bringing out the subsets A. The subsets A. And so the A, they define the elements as 1, 3, 5, and 8. And then B, the elements have been defined. Prime numbers 2, 3, 5, and 7. So those are the prime numbers we have. 2, 3, 5, 7. From 1 to 10, those are the only prime numbers. And prime numbers are numbers that have two factors, itself and 1. It means nothing divides them except itself and 1. So those are the prime numbers we have. And then the C has been defined. C. Alright, defined as 2, 3, 8, and 10. 2, 3, 8, and 10. So understand that even before we solve this, we can decide to represent this information in a Venn diagram. But Venn diagram, no, we are not going into that today. So we just have to go ahead and solve the solution. So I part, they say we should find A union B all complements. A union B. So the first thing we have to do is to find the union of A and B. Now this is A, this is B. They say we should find the union. Join the elements of A and B together. So you have 1, 2, we have 3, we have 5, we have 7, we have 8. So we have A union B. A union B, we have joined the elements of A and B. So we have the union. But they said all complements. So we can now say, therefore, A union B all complements. Meaning that if you remove these elements from the universal set, what will be left? If I remove 1, 2, 3, 5, 7, 8 from the universal set, what will be left? So 4 will be left. 4 is missing here, so 4 will be left. 6 is missing, so 6 will be here. 9 is missing, and then 10 is missing. So the complement of A union B. So A union B gives us this, and then the overall complement of A union B will give you this. It means the elements you find in the universal set, and you cannot find them in A union B. That's the first one. Now the second one, we'll be asked to find A complement intersection C complement. So the first thing we need to bring out is our A complement. A complement. This is A. The complement of A means if we remove 1, 3, 5, and 8 from the universal set, what will be left? 2 will be left. 4. 6 is missing. 7 is missing. 9 is missing. And 10 is missing. It means if we take out 1, 3, 5, 8 from the universal set, the complement of A will be 2, 4, 6, 7, 9, and 10. That will be what will remain in the universal set. And then after that, we'll now go into the C complement. C complement. Meaning that we should take this element C from the universal set. What will be the complement? So 1 will be the complement. 4 will be missing. 5 is missing. 6 is missing. 7 is missing. Then 9 is also missing. It means that if we remove 2, 3, 8, and 10 from the universal set, the leftover elements will be 1, 4, 5, 6, 7, and 9. And that will be the complement of C. Therefore, A complement intersection C complement, meaning that the A complement and the C complement, what are the intersecting elements? 4 is intersecting. After 4, 6 is intersecting. After 6, 7 is intersecting. And then 9 is intersecting. It therefore means that A complement intersection C complement will give us 4, 6, 7, and 9. Now we are going into the third one, which is B complement symmetric difference C. Alright? So B complement symmetric difference C, that will be the third one, I. So to get that, we bring out B complements. So our B complement are the elements missing in B but in the universal set. 1. So we have 2, 3, we have 4, 6, 8, 9, and 10. Now we have B complement. So we bring out our C. And our C is giving us 2, 3, 8, and 10. 2, 3, 8, and 10. So when you have your B complement and your C, now they want us to find the symmetric difference. The first thing is to look for their difference. B complement difference C. And then C difference B complement. Those are the two things we need. The difference. So what are the elements in B complement but not in C? The elements in B complement but not in C. 1, 4, 6, and 9. So those are the elements in B complement but not in C. So the next thing we do is to find the elements in C but not in B complement. The element in C but you don't have it in B complement. And that will be 2, 3. And that's all. So 2 and 3. So B complement difference C is this. C difference B complement is this. So what will be the symmetric difference? Therefore, B complement symmetric difference C. And when we have symmetric difference, it means we unite the two. So that will give us 1, 2, 3, 4, 6, and 9. So that is our B complement difference C. And then finally, the last one, IV. So they say we should find A intersection B intersection C. That's the intersection. So we are going to look at A, B, and C. What are the elements intersecting between A, B, and C? You can have it here, 3, 3, 3. Any other elements? No. So the only element that is found both in A and in B and in C is only 3, 3, 3. So the A intersection B intersection C will just be the element C. So that's where we are going to stop today. Time has really been far spent. When we meet next, we'll be going into the power set and Venn diagrams. So please, I would love you to also subscribe to this video and then click on like if you enjoyed it. And if you have any question whatsoever, please drop your comments in the comment section below and we'll answer your problems. We'll give answers to every problem you have. God bless you and see you in the next set theory 3. Cheers.